Assalamu alaikum, Shabab. Welcome back to the class. I updated my slides. I added few equations in one section, but now we'll talk that something we will consider later. Don't worry about it. I will update the slide in the blackboard as well. But for now, we stopped at this problem, the one you are seeing in front of you right now. And we're just gonna get to the solution. Just give me 1 second. Okay. So let me summarize this problem for you again, okay? And then we will start solving it. Now, what we have here is a square thread power screw with a diameter, which is a major diameter, equals to 32 millimeters, and a pitch size of how much? 4 millimeter. And we have N, which is 2, because it is double threading. And we have been given F, which is equals to F for the collar. So the friction between the screw and the nut, and the friction of the collar, okay, with the platform is equal to 0.08. And then we have the diameter of the collar, which is equal to 40 millimeter. We have an F applied on each screw, so there seems to be many screws, which is equals to 6.4 kilonewton. And we want to know what is the depth of the this is the width, this one is the depth of the thread, and we want to know the pitch diameter, the minor diameter, the lead, the torque. So let me just start one by one. The diameter, the mean diameter, so maybe I should now switch to a different color just to feel that this is the answer. So the mean diameter, as we illustrated previously, is the diameter which is the average between the major diameter and the root diameter, okay? Now, this is dr, this is d, and the mean diameter is in between, right here. This is the mean diameter, dm. And what do we have? We have dm, which is equal to what? Now, if you recall from the diagram that we showed you about how the thread is being cut, this is P over 2, and this one is also P over 2. It's a square. It's a square threading, and if you cut half of this one is going to be, this distance now is going to be P over 2 divided by 2, which is going to be P over 4. Now, and so if you calculate this small distance, this is P over 4, and the small distance here also between the middle of the thread to the root is also P over 4. So you will get 2 P's over 4. And that's why, okay, that's why, ya shabab, you will see that the mean diameter is equal to the major diameter, this one, and then you take a little bit from here, a little bit from here. These two parts are P over 2 and P over 2. So we have, no, P over 4 and P over 4. So this one is going to be P over 2. Why? Because it is D minus P over 4 minus P over 4. 2 p's over 4 is p over 2. ربعين يا شباب يساوي نص. انتهينا. So what are you going to have? You're going to have 32 minus the p is 4. So this is 4 over 2, and it's going to be 2. So the mean diameter is going to be 30 millimeter. Okay. What is the root diameter? dr. dr basically is this the major diameter minus the depth of the thread. The depth is b over 2, and you have two depths from both sides, and for that reason you will get d minus how much? Minus p. This p is coming because we put p over 2 minus p over 2. 2 halves. It's 1. So how much is going to be? This is going to be, it's minus 4, so it is 28 millimeter. Okay. Now, what is the lead? We talked about the lead, but we never gave you an equation. So this is the equation for the lead. The lead L is equal to the number of the threads multiplied by the pitch. You understand? So if you have single threading, N is 1, double threading, N is 2, triple threading, N is 3. So this is 1 multiplied by the pitch. So the pitch is 4, and this is going to be 4 millimeter. معناها this power screw will advance 4 millimeter in the direction of the nut when you rotate it one single rotation. One single rotation. Understood, ya akhwan? Okay. Now, if you have any question, you can interrupt me anytime. Now, the next thing is to find TR, the raising torque. TR equation is F multiplied by dm. Of course, we know F, we know dm, divided by 2, multiplied by L plus what? By F dm divided by dm minus F is the torque which is needed. Now we have a collar, and if we have a collar, we need to add the collar torque. The collar torque, if you remember, was F multiplied by F collar multiplied by D collar divided by 2. You need to add it always to the torque. So if you want to find TR, that is 6.4, that's in the force in kilonewton, multiplied by the diameter, mean diameter, which we calculated, 30, divided by 2, multiplied by, I think I will run out of space here. This is 8. What is 8? Did I? No. Sorry, ya shabab. I forgot one thing. Here, this was 2. I don't know why I put 1. We have 2. This is N. And this one is 8. Sorry about this. So what do we have over here? We have, I think I'm going to rewrite this down. It's not going to work out here. Okay. So we'll have TR equals to 6.4 multiplied by 30 millimeter divided by 2 multiplied by 8, the lead, plus by multiplied by 0.08, which is the friction. The friction was given to us, multiplied by 30 again, which is dm, and then this is divided by multiplied by 30 minus 0.08 multiplied by 8 plus the force 6.4. Now I am talking about this part, the force multiplied by the diameter of the collar was given to me. How much was it? It was 40. And then the friction of the collar is 0.08, which is the same as the friction between the screw and the nut, divided by 2. How much all of this is going to be? It's going to be 15.94 plus 10.24, which is equal to 26.18 Newton meter. Okay, Shabab. Now, what is TL? The lowering torque. Okay. Now, the lowering torque, as we get it from the equation, is F multiplied by dm divided by 2. And then we have by F multiplied by dm plus, minus the lead, okay, minus the lead divided by dm plus F, the friction, multiplied by the lead. And again, while we are lowering or raising, we always have to add the Kohler torque. So plus F FC DC over 2. Now, how much is this one? The lowering torque, TL, is equal to, again, 6.4 kilonewton multiplied by 30 millimeter divided by 2. And then I have by the friction point A, 0.8. Then I have 30 minus 8 divided by 30 plus 0.08 multiplied by 8. 8 is the lead, Yashab, don't forget, plus 6.4 multiplied by the friction 0.08. No. Multiplied by the friction. Come on. I need to go down. This is just... So it is 6.4 multiplied by 0.08 multiplied by 40 divided by 2. Now, if you notice over here, you will get the lowering torque, ya shabab, is going to be how much? Minus 0.466. So there is a problem over here. This is not self-locking. This is not self-locking. 0.466 plus the torque is 10.24 from the Kohler, which is equal to 9.77 Newton meter. Now look, the minus sign in the first term indicate that the screw alone is not self-locking. And if you put the screw alone, it's not going to be self-locking. لكن because, okay, let me just add your friend over here. However, the Kohler added enough friction in order to make the lowering torque a little bit, above, and it's actually not a little bit, it became 9.77. So without a Kohler, we wouldn't have a self-locking mechanism entirely. Okay, but you have to remember one thing, that the lowering torque here is 9.77, while the raising torque is 26. So you can see how much is the difference, nearly 3 times. Okay, so now the next step is to calculate E, the coefficient of friction, which is F multiplied by the lead divided by 2 by TR, and this is going to be 6.4, the force multiplied by the lead, which is 8, divided by 2 by multiplied by the raising torque, which is 26.18, and how much do we get? 0.311, which is 31.1%. That's the only efficiency that you can get. Okay, now in the question it says find the body stresses, torsional and compression. And what does the body stresses mean? It means that we know that the screw has a body like this, and then it has a thread which is around it. Now the body itself will generate some sort of stresses, and the thread, it's also, because it is carrying a load, will carry stresses, or will generate stresses, I mean. So the body stresses are the torsional stresses. This is the first one. So torque, the shear stress because of the torque, which is 16 multiplied by T divided by dr cube. Now, what is the torque that we are going to use? The lowering torque or the raising torque? Which one?
The lowering.
Why?
Because the minimum. I think.
Anybody else? شكرا يا حسن. Well, yeah, Shabab, we should use the raising torque. Why? Because if I use the raising torque, this is what's going to happen. I will put 16 multiplied by the raising torque, which is 26.18 multiplied by 1,000 divided by, and then I have the diameter, which is 28 cube. Now, what happened over here is that you will get the stress as 6.07 megapascal. This is not a lot, but you can imagine that if you use only 9, then this is probably going to drop by 30. By 3, I mean. So both stresses will be applied. When you raise the screw, you will apply 6.07 of shear stress. And when you apply the lowering torque, you will apply probably around, 2 point something. And the question is, which one we should consider? Is definitely the higher one, because it's going to generate higher stresses. Lower stresses are never a problem. High stresses are the problem. So we will only use the raising torque because it is higher. The next stress is the normal stress, which is equals to minus 4F divided by dr square. Now, how much is this? This is 4 multiplied by 6.4 multiplied by 10 to the power 3 divided by multiplied by 28 square. And this is going to give you minus, sorry, there's a minus here, 10.39 megapascal. Okay. Now, these are the body stresses too. The next, we were asked to find the bearing stress. Now, the bearing stress equation, if you remember, let me just bring the equation in front of me. The bearing stress, 2F divided by constant multiplied by dm multiplied by nt multiplied by p. Okay, now what did we say when we discussed the load carried by the thread? We said that we will, in design analysis, we will focus on one thread which will carry 38% of the load. So this is how are we going to deal with it? We will put a minus. 2 is the same. We're not going to change it, but we will replace F with 0.38F. You understand? And then we will divide by dm1 multiplied by p. So when we put 0.38F down p, in t, we substitute it as 1. So this is going to be equal to 2 multiplied 0.38 multiplied by 6.4, and then we have 10 to the power 3 to convert from meter to millimeter to meter. Is it? No, to make it in Newton. A Newton per millimeter will give you a megapascal. So this is by dm is 30, and then we have nt as 1, And what was P? P was 4, was given to us as 4. So how much is this? This is going to be minus 12.9 megapascal. Now remember, this stress is applied only on one thread. That thread is the one which is going to take the first portion of the load, which is the maximum, 38%. It is not every thread. No, only one. The remaining, the second one, we said will take 25%. The other one will take 12, and so on. So what is then? We were asked to find the stresses at the root. Okay. Now, at the root, we know that the most important stress is the. At the root we have one stress, which is what? The bending stress. ليه يا شباب؟ لأنه in the root over here, we have sigma bending, but we don't have tau, which is equals to 3v over 2a. It is maximum down. At the root, it is 0. That's why we don't care about it. So whenever you are asked about the root stress, then you have only one. Remember, the shear stress coming from torsion also acts at the root. It is on the body and at the root, but we already calculated it. So we don't need to calculate it again. So we will calculate sigma bending, which is equal to, again, the equation is 6F. We will multiply 0.38F divided by dr multiplied by nt, which is 1 multiplied by p. So how much is this? 6 multiplied by 0.38 multiplied by 6.4, 10 to the power 3 divided by the root diameter is 28, nt is equals to 1, and p is equals to 4. And how much is this? It's going to be 41.5 megapascal. As usual, ya shabab. Who's the king? Who's the king? Bending. You will always have to be scared from bending, ya shabab. I mean, look, it's 41. The highest stress we got was 12 for bearing stress. Even the torque, the twisting, was 6 point something megapascal. The normal stress was 10. This is alone. It's like 4 times, nearly 4 times the maximum stress which is we achieved before, which is the bearing. Yeah, nearly. So bending is always the trouble, ya shabab. You have to be very careful. You think that the thread is tiny, and if you think about bending as the force multiplied by the distance as a moment, that distance is too little and the bending stress is not going to go high. You are wrong. Okay, it is more than this. So the question then asks us about the to just say it. It says in the question, determine the von Mises stress at the root of the thread. Again, the root is the dangerous spot. So what are we going to do? We will say sigma x, which is the bending stress, is equal to 41.5 megapascal. Sigma y is the compression coming from the body, which is minus 10.39 megapascal. Sigma z is equals to 0. Tau xy is equals to 0. Tau yz is coming from the twisting of the body, and it is 6.07 megapascal. And then we have finally tau zx, which is equals to 0. Okay. So what do we do with all of this? We say sigma prime is equal to 1 over the square root of 2. And then we have here, first, sigma x, which is 41.5, minus sigma y, which is minus sigma x minus sigma z square plus then sigma z minus what? Minus sigma y, which is minus 10.39 square, plus sigma y, which is minus 10.39 minus 41.5, which is sigma x, also square, plus, just add, okay, plus 6 multiplied by, we have only one shear, which is 6.07 square, and all of this is under the square root. Okay, now if you do all of this, you will get the von Mises stress as 48.7 megapascal. This is sigma prime. Now, if you in the solution of the slide, you will see that the solution also showed you that you can find the principal stresses, okay? And using the principal stresses, you can use von Mises equation, which is a function of the principal stresses, sigma 1, sigma 2, sigma 3. But the question that we were asked, okay, it says that determine the maximum shear stress at the root of the thread. Now, the maximum shear stress, ya shabab, we know that tau maximum is equals to sigma 1 minus sigma 3 over 2. For that reason, okay, we need to find the principal stresses. Now, what are the principal stresses? If you remember, we get sigma x plus sigma y divided by 2. This is sigma 1 and 2, plus minus the square root of sigma x minus sigma y over 2 square plus tau xy square. Now, what is sigma y? This is, look, wait a second, ya shabab. Okay. So what are we going to do? We need to go to the, I'm going to go over here, right there. Now, I want you to focus with me carefully, okay? Very carefully. Now, if you sketch the cube, ya shabab, like this, and as you see, we're putting this as sigma x, this one as, as x and y, and this one is z direction. Good. Now, where is sigma x? The bending is here. So this one is sigma x, which is the same as sigma bending. Good. And then we have sigma y. Let me make it maybe in green. That's sigma y, and it is coming from compression. So sigma y is like this. That's sigma y, which is sigma normal, okay? And then we don't have any stress in the z direction. Now let's look at tau xy. You remember tau xy? Tau xy is the stress going in the x phase in the y direction. We don't have it. And we have here only one shear, which is tau yz. Now, tau yz, ya shabab, is going in this direction. This one is tau yz. It is acting in the y phase, and it is going in the z direction. Good. Now, look what happened, ya shabab. Okay. What is sigma x? What is it? stress, the normal stress, which is acting in the x direction, what do we call it? If there is no shear acting on it. لاحظ إنه this is gonna go like this. الX face ما في shear stress. What do we call it? This is way back in chapter 3. You already forgot it. Or nobody is paying attention.
Oh, I think we forgot it.
Yes, Doctor. Yeah.
If you remember it, you forgot it. That's right. But if you understood it, you will never forget it. Any plane, يا شباب, like this, which has no shear stresses, is called the principal plane. Do you understand that? Sigma x is actually a principal stress. Do you get what I'm talking about? So what happened over here is that this x is a principal. We don't need to worry about it anymore. We don't need to calculate it. Sigma x ما دام انه شغال على face which doesn't have a shear, it's a principal. It's over. Now, what do we need to do? What do you think we should do with the y face? What do you think?
We should calculate the principal stresses.
Yes. لكن انتوا يا شباب اذا تذكرون احنا ايش كنا نسوي؟ Sorry. We go and take one face and we think انه there is sigma x, there is sigma y, and then there is tau xy like this. Do you understand? Now, with sigma, if you look at the face of y, okay, it has sorry, Ashab, not this one. I'm sorry. What are we gonna do now? If you look, we are gonna take this face. Is this true? We're gonna take this one. Or should we take this one? Which face should we take?
The first one. Because if we take the face on Y, we cannot draw the sigma Y. It will be inside the paper.
Okay. So which face should we take? We should take this one, right?
Yes, the face.
Okay. And if we take this face, what are going to be the stresses?
Only sigma X and sigma Y. Only sigma Y.
What about sigma X?
It's already principal.
Shouldn't we take the right one? The normal to the x. So we can have tau yz and sigma y.
Yeah, you should actually take this face, correct? Do you see this? When you take that face now, the green one, okay, the tau is going to be like this and like this. And now sigma y is going to be like this. That's sigma y. This one is tau yz. Do you see this? Now, if we do this, what will happen? We will have only sigma y. And sigma x, we don't have a stress. So we will end up applying sigma y, which is going to be minus 10.39 divided by 2 plus or minus, then we will have minus 10.39 divided by 2 square plus tau xy, which is how much? It is 6.07 square. And if you calculate this, you will find the principal stresses to be 2.79 and minus 13.18 megapascal. So as you see, we have the first principle, which is 41 point how much? 5. This is sigma 1. Sigma 2 will be equal to 2.79, and sigma 3 is going to be minus 13.18. So you apply this here, you take this one here, and you get the maximum shear, which is going to be 27.3 megapascal. Understood, ya akhwan?
Yes.
Okay, I hope so. That's a tricky one, a really, really tricky one. It requires understanding. Another thing, إذا أنت الآن في chapter 8, chapter 8, and you think إنه anything related to chapter 3, you forgot it. Unfortunately, that's the exam is not comprehensive in the sense that we are going to bring you a question about Mohr circle. We are not. But this idea of knowing where the stresses are, if there is a face which no shear stresses are acting, they're supposed to be principal. We can't stop asking you this. بعدين تجي تقول, oh, this is not comprehensive. You should not give us a question like that. We can't move on. Okay, I hope so. You understand the shabab. Now, what are we going to do? We talk way longer than what we are supposed to. And I think we're going to get late again with the material. But now we are going to go to, خلاص, this is all for power screws. Now, we are going to go to threaded fasteners. Threaded fasteners are those friendly guys. You see them? Different over there. Sorry. These are the threaded fastener. Very, very familiar. And we have this hexagonal nut and a screw with this thread. Very famous. This kind of screw also very famous. You can go to the market and see it. They are very cheap as well and abundant. Okay, this one is the one that uses Allen key with a hexagonal socket to push it in, and then you start to lock it, unlock it. As you see, those fancy nice drawing has dimensions: L capital, L small, D, D, D. This is H. There is an angle. In general, we call the length from the beginning, just below the head. This one we call it the head. The length from here to there we call it capital L. This length include a part which is not threaded. We usually call it the shank, and a threaded part. And the threaded part, the length of that threaded part, we call it L, or as we're going to see, we're going to call it LT. Sorry, it's going to be called LT or L. We're going to see later. So there are specifications about how much is this length, the threaded part. So in general, you should understand that that these little screws, which I told you, very common everywhere in the market, they are not, made by random. There are standard. Okay. So for example, if you want to know how much is supposed to be the threaded part of a screw, then you should understand that. Just wait a second. Okay. So the length of the threaded part is not made by random. There are governing relations. So in metric, for metric bolt, the length of the thread L capital is equal to twice as the diameter of the bolt. So the bolt has a head and it has a rod which is threaded. This rod has a diameter d, small d. Now, you multiply this diameter by 2, and then you add to it 1/4. This is in inches. For any bolt which has a total length less than 6 inches. If the bolt has a length of more than 6 inches, then you multiply the diameter of the bolt by 2 and you add half to it. The total is going to be the total in millimeters. So I said this is in inches, right, by 2, and you add 6. If the total length of the bolt, and we said that the total length is this length, okay, is less than 125 millimeter, and the diameter is less than 48 millimeter, you add 12 if you have a range between 125 and 200, and you add 25 if the length of the bolt is more than 200 millimeters. Now, where D is called the nominal diameter. And we will tell you, as I indicated here, what is the nominal diameter later, precisely. But these equations are very important because they will teach you anything, يا شباب قحطاني.
Doctor, the difference, the L in the range is, you said L total is the rod, but L in the range, is it the whole bolt?
No. Mani, this one is called the threaded length, L capital. Okay? The threaded length. I am going to talk about the details in a little bit. Don't worry. There is a very nice detail about it. And this is, sometimes of screws. We're not going to spend a lot of time talking about them. There are too many types. Okay? Now, what matters is that you should know that we have different screws. Sometimes we don't have we don't have a shank, we have all threaded, sometimes not, as well as we have the famous hexagonal nut. Hexagonal, because it has 6-sided, okay? And we will see that this hexagonal nut has certain dimensions in terms of width and height, and we're going to talk about them later. Now, what is important is that the purpose of those threaded fasteners is to join two members together, clamp, okay? And what happened is this drawing is showing you what's supposed to be something like this: a flange, which is a round disc with holes on it, okay? And then a pipe like this. Now, this pipe is very common. You can see it, for example, in the pipeline. Sorry, ya shabab. This is supposed to go, like this. Okay, let's assume that this is a pipeline, and there is an opening in the pipeline for measurements. So the fluid is inside over here. Of course, if you let it be open, the fluid will go out. So what do? We take the flange, okay, and then we bring it on top over here. And then what happened? These bolts, طبعا هذا cross section, will be used here to clamp it. So from the top, you have too many bolts, but from the side, you have only one. Now, there are two ways to clamp this. The first one is to bolt up. This is the flange and this is the pipe, two pieces, different colors. They can be made from different material. And if you are lucky, as we will see, they can be made from the same material. Most of the time, same the material. Now, you can put a bolt like this, and then you put a nut. And for some purposes, we are going to talk about them later, you can also put washer. Look, there is a washer here. And then you screw. And when you screw, what happened? You will provide a clamping force. الكلامبنج فورس ايش هدفه يا شباب؟ انه المنطقة هذه الفلويد ما يجي من برا كذا ويطلع برا. This could be very dangerous fluid or gas that kills people, or it's flammable, it just burns. So there is another way. The other way is to have a bolt, and then this part of the flange, or the pipe, I mean, is threaded. So when you screw, the bolt goes through the thread, and then what happened? As you screw, the bolt goes down, and the member is being pushed up. And by that, you will have a clamping force. هذا يا شباب is a ceiling. Why? Because sometimes the connection between metal and metal is never going to be enough. There are always a little bit of, you know, ups and downs and valleys. And so what do? They put a ceiling right here. A ceiling يا شباب يكون زي الربر. And when it is pushed, okay, it will provide, it deforms and it seals the area. So fluid cannot go out. Do you understand? Now, what are we going to focus on is very important. We're going to think about two plates together. They may have the same material. They might be made from the same material. They might be made from the same thicknesses or different thicknesses. But what are we going to imagine? That we are going to put washers. Sometimes we don't put washers. And we are going to put bolt in here. And we are going to have a nut on top and on the bottom head. And these guys are screwed together. And we will assume that the pressure of the fluid, okay, is gonna push up, trying to split this open. So the reaction will be down like this. Sometimes you have things clamped together and they are, you know, being pulled apart. The purpose of the bolt إنه هو يجمعها. The external load is trying to crack it open. Do you understand? Now, what are we going to do is this. We need to understand what are the parts that are inside the grip and the part which are outside. Sometimes we have a little bit of the bolt is outside and the majority of the bolt is inside. Now, if you screw the nuts over here in the head, you can imagine that all the stresses are generated in here and no stresses are here. And we need to understand, is it threaded? Is it not threaded? And so on. Okay, we'll talk about this next class, inshallah. Don't forget that the quiz has been delayed. I need to take your attendance, Shabab, in 1 minute. So please turn on your webcams. Okay, where are you, ya Shabab? We have Faisal. Faisal? Yusuf? Yusuf? Hamid?
Yes, Hamid.
حمد. علي القحطاني؟ علي؟ يوسف؟ يوسف؟ Okay, it seems like people are either asleep or they are not here. ماجد العباد I can see him. حسن العلي حسين العلي.
Yes.
يا محمد.
Yes.
حسن العياش.
Yes.
مبارك دوسري. مبارك. احمد غزالي. يا علي.
موجود دكتور.
معجب. سلطان. سلطان الحربي. عبد الله. حجاب.
Yes.
سلطان.
Yes.
روشان. سير. عبد الرحمن.
Yes.
خالد العتيبي.
موجود دكتور.
عبد الله العوفي.
موجود.
فارس قحطاني.
موجود دكتور.
ثابت.
حاضر.
اوكي. رمضان علي.
موجود
سير.
دكتور.
هاشم.
موجود.
ماجد.
يس دكتور.
محمد.
موجود دكتور.
احمد سلطان.
يس دكتور.
مشعل يامي.
يس دكتور.
وليد.
يس دكتور.
محمد بارشيد. محمد. عبد الله سفياني.
يس دكتور.
احمد.
يس دكتور.
اوكي ثانك يو سو ماتش يا شباب.
Excuse me, doctor.
يس.
يوسف.
وين يا يوسف؟
توني بسكر بس وسمعتك تحضر. 10:50.
دكتور also محمد بليز.
محمد هو.
محمد بارشيد.
anyone else؟
دكتور أنا مسكين الساعة 12.